here we have the double angle identities. So if you have sine of 2 times an angle, that can be written as 2 sine theta cosine theta. And if you have cosine of 2 theta, that can be written as cosine squared theta minus sine squared theta. So here's 2 of the ones that you have to have memorized for tomorrow's quiz. So make sure that you just have both of these memorized. Okay, let's look at what types of questions you might be asked on the test for these things here. So, the function k is given by k of x equals 4 cosine of 2x. Which of the following is an equivalent form of k of x? So when I see cosine of 2x, I'm thinking about the identity that I can use, because if I look, do I have a 2x on any of these here? I do not. So they used that double angle identity to get rid of the fact that there was a 2x. So that identity was that cosine of 2x is cosine squared x minus sine squared x. Is that an answer choice? No. And I can distribute my 4, and I get 4 cosine squared x minus 4 sine squared x. And that is almost an answer choice. But is it the same as answer choice D? No. There's a plus sign right there in between. So in fact, I pretty much know D's out, because I can't just change a plus sign to a minus sign for no reason. So, I see 8 sine x cosine x. I don't think that's it, because what is your identity for sine of 2x? 2 sine x cosine x. I think right there, they're trying to get you to mess up and use the wrong one, right? That's what I think. So, I don't think it's going to be that. When I look at B and C, I notice that there's only cosine, right? No sines. So, one of those strategies that we've been using on our other problems is that sine squared x equals 1 minus cosine squared x, or that cosine squared x equals 1 minus sine squared x. These are just variations of the Pythagorean identity that we have. So I can change everything to sines or everything to cosines here if I want. I would go with cosines, because answer choices B and C have cosines, right? So if I get rid of sine squared x, I can replace it with 1 minus sine. Cosine. Sorry, it won't let me erase right here. Cosine squared x. So then, if you have this, you would need to distribute that negative 4. So I've got 4 cosine squared x minus 4 plus 4 cosine squared x. Still not an answer choice, but do I have anything that I can combine here? Those cosine squared x's can be put together. I've got 4 cosine squared x plus 4 cosine squared x. That is going to give me 8 cosine squared x minus 4, and that is answer choice C. Mm-hmm.
How do you actually plug the double angle into the equation?
We know that this right here, right, on the slide before, it tells us that cosine of 2x equals cosine squared x minus sine squared x. There might be thetas there, but they're using x's in this problem. So I can take this out, and replace it with cosine squared x minus sine squared x.
Are you able to do that all the time or just at the start of the equation?
Anytime. But it has to be a cosine of 2x. It can't just be like cosine x. We can't replace that. It has to have 2. Oh, that's a good question. I don't think it applies if cosine is squared there. So, like, you would need to just have regular cosine of 2x. The only ones that really, anything that has a plus or minus anywhere in the identity does not really apply unless it's exactly as it looks. If you have like the reciprocal identities and those sort of things, they can still apply if you're squared, third power, fourth power, fifth power. But if it's got a plus or minus anywhere, it has to be exactly like it looks. Yes? I took the 4, so when it's really important when you plug things in, you must have parentheses around them, right? So when I took out the cosine of 2x and replaced it with cosine squared x minus 4 sine squared x, this 4 that's out front has to get distributed to both of those there. So you distribute here and get 4 cosine squared x, and you distribute here when you get 4 sine squared x. And then the same thing happens here. Whenever you replace, like you're taking sine squared x, you're taking it out, you're replacing it with 1 minus cosine squared x, you have to have parentheses there. So this 4 gets distributed here as well. Does that help? Okay. All right, let's keep going. Let's try another one. So this one says, which of the following is equivalent to the expression 2 sine of pi over 14 cosine pi over 14? And these will be calculator inactive problems. So typing it into the calculator to see which ones match is not going to be an answer or a way to do this problem. So here, they don't tell you that like this is a double angle identity. But what we should be sort of picking out is I've got 2, and I've got sine of something and cosine of something, right? That looks a lot like our identity that we have over there. 2, well, all right, like this. Sine of 2 times theta equals 2 sine theta cosine theta. It's cosine. It's not very pretty. So what I'm looking at is like the right side of that equation, right? I've got 2 sine of pi over 14 cosine of pi over 14, right? So this looks just like my identity, except for instead of having the theta, I've got pi over 14, which means that my theta is pi over 14. Which means that I could put that here, right, for my theta. So if I do that, I could write it like this, sine of 2 times pi over 14. And you'll notice that's not an answer choice, but if I make this a fraction by putting it over 1, then that is sine of 2 pi over 14, and 2 pi over 14 reduces to pi over 7. So sine of pi over 7, answer choice C is going to be our answer. So on that one, you got to kind of recognize that you're looking at the identity and go back to the theta on that. Okay, questions there? All right. Okay. The figure shows a circle centered at the origin with an angle of measure theta in standard position. The terminal ray of the angle intersects the circle at point P. coordinates of P are 5, 12. What is the value of sine 2 theta? Okay, so I know, right, it's one of my identities that sine of 2 theta equals 2 sine theta times cosine theta. What would I do to find sine of theta here? We need to use that 12. Okay. We do need to know the hypotenuse of this triangle. Do we know the hypotenuse? It's not 1. Because is this the unit circle? It's not. It's not the unit circle. But they have marked right here that this point right here is 13. Right? So the hypotenuse of that triangle is 13. And so if the x-coordinate is 5, that means you go over 5. You can do 5 squared plus 12 squared equals 13 squared, but you have to square root that 13. So if you use Pythagorean theorem instead, you're doing 5 squared plus 12 squared equals c squared. So you'll have 25 plus 144 equals c squared. And then that will be 169 equals c squared. But the last step would be that you have to square root both sides, so you'll get 13. And since it's marked here, just use the number that they give you for that. So if this was the unit circle, we could just use the x-coordinate and the y-coordinate, right? We would not have to think about the hypotenuse of that triangle. But in this triangle, sine of theta is opposite over hypotenuse. So sine of theta would be opposite, which is 12, over 13, right? So I've got sine of theta is 12 over 13. What would I get for cosine of theta? That is adjacent over hypotenuse. Adjacent over hypotenuse? 5 over 13. So for this, we're doing 12 times, like I'm going to put that over 1. So 2 times 12 times 5. 12 times 5 is 60, times 2 is 120. And then 13 squared is 169. There, so that would be our value. The reason that we don't use the unit circle here is because it's not a unit circle. Like they have told us it's a circle centered at the origin, angles in standard position, which all sounds unit circle stuff, but the radius of this is not 1. So it's similar. You're still kind of using the unit, like it's kind of like the unit circle because the x-coordinate still is part of cosine, right? And the y-coordinate is still part of sine. Another way you could think about this is when we don't have a unit circle, your x value equals r cosine theta, and your y value equals r sine theta. Right, we learned that back in the last unit. So another way you could think of this is that, like, the x value, which is 5, equals the radius, which is 13, times cosine of theta, and you could divide both sides by 13. So that's another way that you could get that cosine of theta is 5 over 13. And then you could do the same thing with that sine there. So that's also an option. Okay? All right. Let's look at these. So far, we've just been using these identities, right? So, like, when I see this, the first thing I want to do is change that to 2 sine x cosine x. However, on some of these problems, that's not very helpful. Okay? So you may not even want to write this down, or if you've got room, you can, and then we're going to cross it out. So, like, if I change this to 2 sine x cosine x minus 1 equals 0, I can't really do much with this, right? I could move the 1 over and divide by 2, but then it's sine x times cosine x, which is not all that helpful. Can I factor that? Can I factor 2 sine x cosine x minus 1? No, I can't factor it. There's no greatest common factor. There's no squares. I can't factor it. So it actually is sort of a dead end to use the identity on this problem. Instead, here is what we want to do. Okay, so we do not want to use the identity. We got sine of 2x. I'm going to put parentheses just because I like to there, but you technically don't have to have them. I'm going to add 1 to the other side. Okay, now, this says to solve for principal values of x. If you guys remember back to whenever we were looking at inverse trig, right? For sine and tangent, it was the first and the fourth quadrant, it was negative pi over 2 less than or equal to x less than or equal to pi over 2, right? So when you see that phrase principal values, that's what they're referring to. We want the answers between negative pi over 2 and positive pi over 2. If it were cosine, then you're looking at the first and second quadrant, 0 less than or equal to x less than or equal to pi. But for this problem, we have sine, so we want to use those values. So what I need to think about now is the unit circle. I need to think about where on that unit circle does sine equal 1. Ignore the fact that it's 2x for now. Okay? So on that unit circle, sine, which is our y coordinate, is going to equal 1 right here. And that is at pi over 2. So I know that sine equals 1 at pi over 2. You can almost think of it like this, although you have to be a little careful with this reasoning. You are like doing the inverse sign on both sides, which means where does sine equal 1? Sine equals 1 at pi over 2. But on the inside, you've got 2x. Right, so there's a 2x equals pi over 2, not just x equals pi over 2 like it's been on all the other problems that we've seen. So if I want to solve for x, what one more step do I have to do? Divide by 2. And so if I divide by 2, right, that's like 2 over 1. Dividing fractions is easy as pie. Flip the second and multiply, and I get pi over 4. So x is going to equal pi over 4. For some of these, you will need to look at, well, for all of these, you need to look at, see how we like divide by 2 at the end? That takes all of our answers and like cuts them in half. So if you have a 2 right here, you need to look at like twice the domain, because in the end you're going to be dividing by 2 and it's going to cut everything in half. So rather than looking from negative pi over 2 to pi over 2, you want to look from negative pi less than or equal to x less than or equal to pi right here, because you've got a horizontal compression that's squishing this in. But does sine equal pi over 2 anywhere else on the unit circle at all? I'm sorry, does sine equal 1 anywhere else on the unit circle? So 1 and negative 1 are the only ones that only show up one time, right? So by extending this, it doesn't actually change anything for these problems. So you would just stop there. Okay. Let's try a different one. Now this time, I've got cosine of 2x. Am I going to be able to do like I did on the last problem where I just basically solve it with the 2x still in there? I cannot, because I've got a sine x over here. I've got another trig function, right? So this one we do want to use the identity for. Okay, so I need to take the cosine of 2x. I need to take it out. I need to replace it with cosine squared x minus sine squared x. Okay, this turns it into something that looked like last night's problems. Am I going to be able to do this one as it is right here? I've got a sine squared and a cosine squared. Is that going to work out for like moving everything to one side and factoring? Can't do it with a sine squared and a cosine squared. Should I change everything to sines or everything to cosines? Sines, because I've got a regular sine x right here. I can't change it, right? So I'm going to do 1 minus 3 sine x. And I do not want this cosine anymore. I want to get rid of it because it's giving me trouble. What can I replace cosine squared x with? 1 minus sine squared x. So I replace that. Now I need to just combine some things and see what I can simplify. So I've got, leave this side alone for now. I've got a negative sine squared x and another negative sine squared x. So that's going to be 1 minus 2 sine squared x. And then let's get everything to one side, right? So I'm going to subtract this 1 here. I'm going to add the 2 sine squared x. I chose to go to the right side because I don't like for my squared term to be negative. There, so this is going to be 2 sine squared x. I'm going to put the minus 3 sine x first and then the minus 2 equals 0. You can write it the other way if you want, but we're getting ready to factor it. So it's generally just going to be easier to factor if it's in descending order there. So now when we're factoring this, remember that this is really like 2u squared minus 3u minus 2 equals 0. So I think most of you X method that. So you have to do 2 times negative 2, which gives you negative 4. You're adding together to get negative 3. What do I multiply to get negative 4, but add to get negative 3? We're multiplying to get negative 4. Which, what about signs? Positive 1, negative 4. But I can't stop here. There's one more step on this type of problem. What have I got to do? Divide by 2. This one reduces to negative 2. This one does not. So this is going to factor into 2u plus 1, u minus 2. And really our u's are just signs, right? So I've got 2 sine x plus 1. times sine x minus 2 equals 0. So I need to set each one equal to 0. 2 sine x plus 1 equals 0. Sine x minus 2 equals 0. And so I'm going to subtract 1 from both sides here. 2 sine x equals negative 1. We'll divide by 2. Sine x equals negative 1/2. Over here, I need to add 2. We've got sine x equals 2. Our answers here come from the unit circle. Where does sine equal 2? Nowhere. You do not get any answers there, right? But over here for sine equal to negative 1/2, sine is your y coordinate. You're going to get here and here. There's negative root 3 over 2 negative 1/2. That happens at 7 pi over 6. And then you also have positive root 3 over 2 negative 1/2. That happens at 11 pi over 6. So we will get x equals 7 pi over 6 and 11 pi over 6. Okay, these are like the questions you were doing on the quiz a few days ago, right? But you're adding a couple more steps until you get to the part where you just factor and solve. Okay, questions there? All right, we have 2 more formulas that we must know. Okay, I do have songs to help you remember these here. So for sum and difference formulas for sine, I can't remember who taught me these. I guess it was it couldn't have been Miss Martin. It's probably, I don't know. I don't remember who taught me these songs. But for sine, sine is sort of like an army chant, sort of. So it goes sine, cosine, cosine, sine. The sine of the sine is mighty fine. So that is because you're obviously sine, cosine, cosine, sine. And it says the sine of the sine, the S-I-G-N of the S-I-N-E is mighty fine. That means this sign right here and this sign right here are the same, right? These are the same sign. Notice that I've got a plus or minus here. It stays a plus or minus here. That doesn't mean you'll see a plus or minus in the problem. It means if you have a plus, keep it a plus. If you have a minus, keep it a minus. There. The cosine one is even more fun. The cosine is the cosine conga. So for this song, it helps if you do, you got to do your arms like the conga. That is helpful there. So it goes cosine, cosine, sine. I'm doing it the wrong way. Cosine. Oh gosh, I'm not ready for this performance here. Cosine, cosine, sine, sine. Don't forget to change the sine. So cosine, cosine. Oh, I can't do my arms right. I need to get this together here, or get a video of somebody doing it. But cosine, cosine, sine, sine. Don't forget to change the sine. I can't do my arms. I'm going to practice. Oh, maybe I'll do it tomorrow. But cosine, cosine, sine, sine. Don't forget to change the sine. Right here. See how this is flipped to a minus or plus right there? So don't forget to change the sine there. So those need to be memorized. Notice that it goes X, Y, X, Y here, X, Y, X, Y for those. So let's look at a couple problems with this. So here is an example where we have to find the exact value of sine of pi over 12. This is without a calculator, and we cannot use anything but the unit circle values that we know, right? And if I did use the calculator, it would give me a decimal, which is not the exact value. So let's think about the unit circle here. The values I know on the unit circle, I've got pi over 6. I've got pi over 4. I've got pi over 3. I could keep going. But none of those are over 12. But I could make them all over 12, right? I could get common denominators for all of these. And so if I do, to get 12 here, I would multiply by 2 on top and bottom. And I would get 2 pi over 12. And here, I would multiply by 3 on top and bottom. And I would get 3 pi over 12. And here, I would multiply by 4 on top and bottom. And I would get 4 pi over 12. And I could do that to the whole unit circle if I wanted to. You could get a common denominator of 12 for the whole unit circle. It is the lowest common denominator you could use for the whole unit circle. What I'm looking for are numbers I can add or subtract that would give me pi over 12. Now, I could really use any of these. I could use the stuff from the second, third, or fourth quadrant if I wanted, but let's stick with first quadrant if we can, right? So I could do 4 pi over 12 minus 3 pi over 12. Or I could do 3 pi over 12 minus 2 pi over 12, right? So if I write this that way, let's do sine of 3 pi over 12 minus 2 pi over 12, right? But if we reduce it back, this is sine of pi over 4 minus pi over 6. So I can use my sum and difference identity here, right? So this one is the one that's the Army chant. Sine, cosine, cosine, sine. The sine of the sine is mighty fine. So I sing it to myself when I write it down. Sine, cosine, cosine, sine. The sine of the sine is mighty fine. That means this minus right here goes right here in the middle. And then just use pi over 4, 4, pi over 6, pi over 4, pi over 6. And so from here, you're using unit circle values. Sine of pi over 4 is square root of 2 over 2. Cosine of pi over 6 is square root of 3 over 2. Cosine of pi over 4 is square root of 2 over 2. And sine of pi over 6 is 1/2. So I could multiply these together. This is going to be the square root of 6 over 4 minus the square root of 2 over 4. You may see the answer left like this, or they may write it like this since those have common denominators. Square root of 6 minus square root of 2 over 4. You have to leave it like that. You cannot subtract square root of 6 minus square root of 2 and get square root of 4, which would be 2, which will give you 1/2. That's not equal there, so you can't do anything else with that. A lot of times they'll tell you which angles to use so that you don't have to like come up with those values on your own. Okay. All right, so here's another example. This one's a cosine example. Our function is cosine of x plus pi over 3. And they're asking for f of pi over 6, which means we plug in pi over 6, for the x, right? So f of pi over 6 would be cosine of pi over 6 plus 2 pi over 3. Now, I could try adding those together, but I would have to get common denominators, which would be 4 pi over 6. Actually, that'd be 5 pi over 6. This may not be the best example because you could just add those together, get 5 pi over 6, find the value. But sometimes you can't do that. So, and sometimes it may be like the answer choices aren't just cosine of 5 pi over 6. It'll be things here. So I intended for us to use the cosine formula here is what I'm looking for. Is that right? 4 pi over 6, 5 pi over 6. That's on the unit circle. I guess that's right. But let's use the formula because we need practice with this. So cosine is the cosine conga. We got cosine, sine, sine. Don't forget to change the sine. So since this is a positive right here, I need a negative right here in the middle. And then we just do pi over 6, 2 pi over 3. Pi over 6, 2 pi over 3. Now, sometimes, like, you got a multiple choice question, and their answer choices look like this, kind of like forcing you into it, right? Here, if we think of cosine of pi over 6, cosine's x coordinate, that is square root of 3 over 2 at, oh gosh, I think I need my points here. Pi over 6 is here. That is square root of 3 over 2, 1/2. 2 pi over 3 is here. That is negative 1/2 root 3 over 2. So cosine of 2 pi over 3 is negative 1/2. And then sine of pi over 3 is 1/2. And sine of 2 pi over 3 is root 3 over 2. So we end up with negative root 3 over 4 minus root 3 over 4, which it's like you got one here and one here, so it's negative 2 root 3 over 4, and then this reduces to negative root 3 over 2. I need to go back and think about that problem because what would have been quicker is just to add those together, get 5 pi over 6, and look at the unit circle for that. So I either need to make it a multiple choice question where you have to use the difference or pick different numbers there for that. That problem doesn't even have that doesn't even have an expression. So we're done here because you can't do that problem.